Hello everyone, my name is Maria Fernanda Ortega Paez, and today I'm going to present my master research, Plasmonic color generation on surface arrays of nanoparticles, a numerical approach. In first place, I'm going to solve the first question. What is plasmonic color? This type of color belongs to the structural color classification. Structural color, in easy words, is the result of the interaction between light and surface structured at the nano and micro scales. In nature, there exists an extensive biodiversity that obtains colors through structured surfaces. For example, in the wings of butterflies and birds, in these cases, the skin of chameleons, in some shiny beetles, fruits, and flowers. Actually, plasmonic color has attracted a great deal of attention by using environmentally friendly, recyclable materials and generating stable, non-bleaching, viewing angle-independent colors with subwavelength resolution and unlimited lifetime. A very popular example of this type of coloration is present in the Lycurgoscope, which I present this image of Lycurgoscope, or in the stained glass windows of the Middle Ages, which retain their colors to these days. And this is one of the principal characteristics of plasmonic colors. This color is named plasmonic color due to the physical phenomenon that causes it, known as localized surface plasmon, LSP. I show this diagram. This is a diagram for about the behavior of LSP. This phenomenon describes the resonance of coupling of light and free electrons in metal nanostructures. The resonance of this plasmon occurs at a specific frequency that depends on the morphology of the nanostructures. The resonance behavior responds to the selective absorption of light inside the material, which will be seen as the generation of plasmonic colors in bulk. This is the case of plasmonic color and how we can observe. So as we have seen, the surface color is a consequence of the excitation of LSP, which are excited inside the nanoparticles, and their tonality is highly dependent on the optical properties of the metal-dielectric interface and the geometry of the nanostructures where they are generated. Recently, it has been discovered that it is possible to realize plasmonic color printing using laser processing on disordered arrays of nanoparticles. How we can observe in this microscope image, these arrays of nanoparticles can support plasmonic resonance in a bandwidth spanning to the visible spectrum. The random distribution of the nanoparticles increase the probabilities of tuning different plasmonic colors on the same surface by varying the interparticle distance. In this way, surface treatment via ultra-short pulse laser irradiation allows modifying and carefully designed nanostructured surfaces using as main channel the excitation of the surface plasmopolariton, SPP. This plasmon is confined to the surface and can be excited by light scattering due to surface rawness, how we can observe in this diagram. This phenomena results in the confinement of the energy in specific regions known as hotspots. This leads to local heating of the material, which enables merging and reshaping of nanostructures. In this work, we demonstrated a theoretical approach to the laser printing of plasmonic color using random arrays of spherical gold nanoparticles placed on a thin gold film and whose average density can be modified by laser irradiation. The main idea was to propose an optimal design for their fabrication where variation of the radius and density of nanoparticles will allow us to tone different plasmonic colors. In the animation, we can observe one of the results of the simulation performed. What can be observed is the excitation of surface plasmons, SPP, that propagate along the interface as the incident beam travels through a scanning area. As it can be observed, the plasmons are localized around the incident area, and which allows to perform a controlled laser modification. This is the decade of laser modification. The numerical analysis was performed using a multiple scattering vectorial model via surface plasmon polarity interactions due to surface nanoparticles to simulate the excitation and scattering effect of surface plasmon polarity on the nanostructure surface. The system response is analyzed with the dyadic Green's function, which calculates the propagation of the incident file from a source point to an observation point. The versatility of the distance between those points is what allows to model to calculate the interaction in both the near and the far field. So one of the objectives of the investigation was to simulate images of the first harmonic which considered the reflection of the metal surface and the plasmonic response of the nanostructures. These two elements is the characterization of the light reflected by this material, and this reflection spectrum can give us a color result. From the numerical results reflect a spectrum of different surfaces with variations in the density and size of the nanoparticles were generated, and the results were used to calculate the chromatic coordinates with the psi-xy color space. This is a diagram of this system. And finally, a color was associated with the spectral response of the simulated surfaces. On the other hand, second harmonic intensity maps were generated for different polarizations, configurations of the light source. The simulated images closely resemble those obtained experimentally, showing similar sensitivity to wavelength and polarization, as well as to scattering configurations. These results have allowed us to validate the vector model based on the plasmonic response of the material. In conclusion, the result of this research opened avenues for a new numerical analysis technique that facilitates the design of nanostructures for printing plasmonic colors by a laser irradiation. This technology is a promising alternative to replace conventional pigments in many practical applications due to the ultra-thin, ultra-compact, highly durable, and environmentally benign properties of the nanostructures. The full-color plasmonic surface with high saturation, high efficiency, and high resolution can be used in biosensing, colorimetric sensing, high-end displays with low power consumption, and encryption of information, high sensitivity optical data storage, holograms, solar cells, and so on. Well, this is all for my part. Thank you for your attention.